So hello, I'm Valentina. I am a software engineer at Red Hat. I've been using Python for over 7 years. I did some web development using Django. And for the last almost 2 years, I've been working on package management tools on Fedora and Red Hat Enterprise Linux, such as Yum and DNF. They are both written in Python with some parts written in C. DNF actually has much more C code. I'll be giving examples mostly in Yum, but the things I'll be talking about are useful for debugging any kind of applications. I'm sure you're familiar with tools like Yum or similar tools such as apt on Debian-like systems. It's what you use on a Linux system when you want to install some software. You fire up your terminal and you type yum install some package. And then it's Yum's responsibility to do everything that is needed to install that package. Check all the repositories that you have configured on your system. Find the package that you want, then do its best to resolve all of the dependencies. Download all the packages from the repositories and finally install them on your system. It does it all for you automatically, so you don't have to worry about it. And one thing that immediately becomes obvious is that there are really quite a few things that can go wrong. Maybe you're having network problems. Maybe the repository you're using is unavailable at the moment. Maybe the software you're trying to install hasn't been packaged properly. Maybe there's a bug in Yum. Yum itself is not a monolith. It relies on other components. Something to work with network, something to handle repository metadata, something to install individual packages. So localizing the error is the first thing you want to do. Even if you can't fix it yourself, you can file a bug report against a relevant component. Another interesting thing is that Yum's code can be used by other software, sometimes in unexpected ways. It provides an API which other components can use. For example, when you install your Red Hat Enterprise Linux system, the installer actually uses Yum's API. And what's great about Python is that even in a very minimalistic environment, such as a system installer, you get the full power of the standard library, all those batteries included. So if something weird is happening, you're equipped with tools to help you debug it. And one of such tools is PUDB, Python debugger. To start using PUDB, you can add pdb.setTrace call to the source code of your program at the location which you want to debug. When your program gets to this point, it's going to pause and drop to a debugger shell. So here's an example. This is a piece of code from Yum, a function which reads a config file, and I've added here this line, import pdb, pdb.setTrace. So now if I run Yum, it's going to run right up to this point where we have our debugger call, and it's going to pause its execution. So we are now in the debugger shell, and we can run debugger commands. What commands are available for us? Let's find out by using help command. There are not that many commands, and for each one of them, some documentation is available. So for example, let's see the help for list. List source code for the current file. Let's try that. And indeed, if we run it, we can see our code. We can see a little arrow pointing to the line that is going to be executed next. Right after pdb.setTrace call, it's line 1044. To execute the next line, we can use the next command, or just n. Now, one thing to remember about the PDB shell is that pressing enter repeats the previous command. If we press enter right now, the PDB will repeat the n command. So we'll move to the next line. We can list our source code again. We can do it by using list or L command. And we can see that the arrow is now pointing at the line 1046, just as we expected. Now, let's say we don't want to manually execute line by line. Let's say we are just really interested in what's going to happen in line 1050. So we want to let our program execute until it gets to line 1050. And we can do that using break command. or just B. That means a breakpoint. So we say B 1050, and now we can use continue command, or just C, and the program will continue execution until it reaches the breakpoint, and then it pauses again. Now, what I want to do now is I don't want to just execute the next line, but instead I want to see what's happening in this function, get and var function. I want to see how it works inside, so I need a way to sort of step into it, and I can do it by using step command. The step command advances the execution and stops at the first possible occasion. So it stops at the very first line of this get and var function. We can list the code and see where we are right now. It's also possible to navigate the function call stack at any moment. So we can take a look at it using where command. And it shows us the stack trace. With the most recent frame at the bottom, we can see get and var function at the very bottom, read startup config function at the level above, and so on. Moving up and down the stack could be done using up and down commands. Okay, now we know how to navigate around our program, but it's not very useful unless we can take a look at the state of our process, at the state of our objects, because that's the whole point of using a debugger. And of course, PDB lets us do this, so let's go up the stack again. Let's take a look at our code. So in line 1045, we created startup.conf object, and we want to look inside it. We can do that using P command. PDB is able to evaluate any Python expression and print its value. And here on this slide, I'm showing how to use P command, which stands for pretty print, and which gives nicely formatted output. So we see which attributes startup.conf object has. We can print value of each attribute, for example, plugin path attribute. So this is a very handy way to debug problems. Let's summarize what we've learned so far. We know how to advance the execution of the program and how to pause it using break command. And by the way, PDB allows to configure your breakpoints. For example, it's possible to set a condition on a breakpoint. So unless the condition is true, the breakpoint will be ignored. We've learned how to navigate the stack, how to list the sources of the code that is being executed, and how to evaluate and print expressions. Also, I haven't shown this, but it's possible to execute statements, for example, set variables, import modules, and so on. And this allows to debug programs pretty conveniently, and I would also say that it's quite a nice tool to quickly get familiar with the code. Even if you see this code for the very first time in your life, inspecting it using a debugger is very helpful. There are, however, many limitations to PDB, and I have to be honest, I personally use it only when no better option is available. For example, as I already mentioned, to debug Red Hat Enterprise Linux installation process. However, when the environment allows, I use another tool, which is actually based on PDB, and it's called PUDB. You can install it using pip, and then just do import PUDB, pudb.settrace. Here is a screenshot of PUDB. We are debugging the same piece of code as before, but now we don't just have a prompt, but we have a very nice user interface. Most of the screen is the source code of our program. We can move around it using arrows, it's very easy. In the top right corner, we can see all our variables and their values. Below that, we can see our function call stack. And below that, we can see our breakpoints. There's also a built-in command line, which you can use to run Python code in the current context. Navigating here is very natural, just using arrows on your keyboard, and you can move from the source code window to the breakpoint window, to the stack window, and so on. Breakpoints can be easily edited using the special interface. So if you want your breakpoint to be ignored several times, or just run when some special condition holds, you can do it here. For variables, there are some very nice inspection options. You can choose how to show you each variable. You can just show its type, or you can use wrapper function or str function, or you can even specify your own custom function. And there are other options, such as which attributes to show. It's very useful to read the built-in help. You can open it by pressing question mark on your keyboard. And there are global settings for PUDB. When you first run it, you will see this Edit Preferences window. There you can configure stuff like, for example, which Python shell to use. And you need to have those shells installed separately, because if you choose the shell that you don't have installed, then PUDB will just fall back to using the standard classic Python shell. So as I said, this is the debugger that I use on a daily basis, and I really recommend you to try it. Unfortunately, when something goes wrong, using a debugger is not always an option. For example, we often get bug reports which we can't reproduce because they require some specific environment. And we can't always ask the person who reported the bug to debug it themselves. Another situation, maybe you have your application running in production and you can't stop it. You want to have a way of troubleshooting it without stopping it. Maybe you have a program for which you don't even have the source code, but you want to know what it's doing. And that's where strace comes in handy. According to its man page, strace is a tool which traces system calls and signals. So signals is probably something everybody is familiar with. The simple example of a signal is when you press Ctrl+C, it sends interrupt signal to your application. But what is a system call? Man page tells us the system call is the fundamental interface between an application and the Linux kernel. And your application, like any application, cannot do much on its own without using system calls. If you want to print something on your screen, if you want to write to a file, if you want to send data over network, whenever you want to do something in the outside world, you have to ask the kernel to do it for you. The kernel knows how to talk to hardware, it knows how to talk to the network. So it abstracts it away from us, and it also takes care about sharing resources between our applications. User applications are simply not allowed to do anything serious. So we always have to ask the kernel to do it for us. As application programmers, we are simply using Python built-in functions or standard library functions, but they actually invoke system calls for that. And strace is a tool which shows each and every system call that a process is invoking. This is what a regular strace output looks like. And this is just a tiny little bit of output from yum installing a package. It can be overwhelming, so strace has filtering options. But let's first take a look at a very simple example. Here I've written a program which prints hello world, and I'm going to run it under strace. So I first specify an output file for strace using -o option. If I don't do that, then the output from strace will be mixed together with the output from my program. Then I specify the program I want to run, which is Python, and its arguments. We have one argument, it's hello world.py. When I do this, my program runs and prints hello world on the screen, and all strace's output goes to the log file. Now, how big is that file? Turns out on my system it's 1086 lines long. On your system, the number will be different, but that seems like a lot for such a simple program. But turns out that most of this output is not about my program at all. If we grep for string hello world.py, we see that the first time Python even tries to do something with it, it happens in line 1053. We also see hello world.py mentioned in line 1, but what's actually happening there is Python itself being executed in the new process using exec_syscall. And hello world.py is listed as one of the arguments for that syscall. So that's just running Python, that's not running our script. Our script comes into play only in line 1053 for the first time. So everything that's happening before is system calls for the Python interpreter itself. Okay, but what is exactly happening in line 1053? Let's take a closer look at it. So Redlink is the system call name, The values in the parentheses are the arguments that are passed to Redlink function. The part after the equal sign is the return value of the function. In our case, it's -1, and that usually indicates an error. And this part is the symbolic representation of that error. So whenever you see a system call that you've never seen before, a good place to start is reading its man page. You usually want to explicitly specify section 2 of the manual. That's the section for the system calls. So in our case, we type man2 redlink, and that gives us the page for the redlink system call. If we hadn't specified section 2, that would have given us man page for the redlink shell command. So we get the man page for redlink, and redlink adds system calls, and it says that what these system calls do is read the value of a symbolic link. Then in the synopsis section, there's the function signature in C. Let's take a look at it. Here we can see which arguments Redlink function takes. So we now know that the first argument, this string hello-world.py, is the path name. The second argument is buff. It's a hexadecimal number which represents an address in memory. And the third argument is buff size. And it has type size t, and it's basically an integer. We also see that the return value has type as size t, and it's also an integer. So let's go back to our man page and let's read the description part. It says, Redlink places the contents of the symbolic link path name in the buffer buff. Okay, that makes sense, but we know that hello-world.py is not a symbolic link, it's a regular file. So the function fails and it returns an error. And the man page contains the description of return values. On success, these calls return the number of bytes placed in buff. On error, -1 is returned, and RNO is set to indicate the error. So that's exactly what happened, and now we know how to interpret that error value. It means the named file is not a symbolic link. Strace is really trying to be as helpful as possible when presenting its output. It shows structures with labeled fields. It shows strings. It shows arrays. It shows exactly which error happened. It shows flags, not as numbers, but as their symbolic names. It's really trying to be readable. It's good if you can read Gcode. It's good if you understand system programming, but even if you don't, you can still understand what's happening in general. And there are always man pages available. So which system calls does an application like yum invoke? Here I have a command. We are going to trace the execution of yum install zish command, and we want the output to go to network.strace file, and we use -f option to trace all the child processes and threads that get created, and we only want to see the network-related system calls. And we use -c option to print the summary, and -S option to sort the output. In this case, we are going to sort the output by the number of times that each system call has happened. So this is how the summary looks like. The most frequently used system call is receive from, and that's what we would expect because we download a package and we are mostly receiving data. Names of these system calls are pretty self-explanatory, and you are probably familiar with them if you've ever worked with the socket module from the standard library. Another example, let's trace all system calls which take a file name as an argument. There's more variety here. Yum does a lot to your files. There's renaming, and there's unlinking. There's creating new directories and changing file permissions. The most frequently used system calls are stat and open. Stat as well as lstat in the third line returns information about a file, and open, as you can guess, opens a file. But notice that there isn't a single one read or write call in this summary. Why is that? Well, that's simply because we were tracing calls which take a file name as an argument, and system calls for reading and writing to a file don't require a file name. Here's an example of the open system call. Its arguments are the file name and the flags, and what it returns is a number, in this case number 3, and that number is called a file descriptor. And that's what gets passed to read and write functions. So whenever you go through an output of strace and see a read system call and you want to know which file is being read, then you should look at the file descriptor that is being used and find the open call which returned this file descriptor. The same goes for the write system call. In this case, it gets file descriptor 1, and that is the file descriptor that is reserved for the standard output stream. Each process has its own table of file descriptors. And normally, even if the process doesn't open any files, it has file descriptor 0 for the standard input stream, file descriptor 1 for the standard output, and 2 for the standard error stream. So unless we redirect the standard output stream, writing to the file descriptor 1 will print to our terminal. Actually, for convenience, there's the -y option, which prints the full path associated with each file descriptor. So here we see that strace shows both the file descriptor number and the full path of that file. So how can you use strace in practice? Well, as we have just seen, you can use it to see which files your application opens. For example, to find out exactly which config file it uses. That's a common use case for troubleshooting. You can get some idea about behavior of an application for which you don't have the source code. And it's useful if there is no documentation. Or maybe you don't trust the application, you suspect it to do something malicious. Which files does it open? Which network connections? There's also a useful utility called lsoff, which gives you a list of open files for the process with a specified process ID at this exact moment. And here the word file is used in its Unix meaning. As we know, everything is a file on a Unix-like system. So lsoff output will not only show you regular files, but also device files, sockets, pipes, and so on. You can use strace to reason about what your application is doing while it looks to be stuck. That's probably one of the most common use cases. You can see whether it's waiting on the network, doing I/O, or waiting on some resource that is locked. Maybe it's not doing any system calls, and that means that the process is doing something purely computational at the moment. So strace removes a lot of guesswork. And what's really great is that you can attach to a running program using -p option. That will make strace attached to a process with a PID that you specified, just as we've seen with lsoff. Attaching strace to a process will affect its performance, but it won't pause the execution as a debugger would do. So you can do it even if you can't afford to pause your application. You can use strace as a simple traffic sniffer to see unencrypted network traffic. That can reveal problems with your server configuration or network protocol implementation. There are a couple of useful options to remember here. Y option will print the IP address and the port number for each socket, and S option will show you, it will allow you to specify a number of bytes to print for each string, because by default strace just cuts each string and prints only the first 32 bytes. There are some other more advanced applications for analyzing network traffic, like TCP dump and Wireshark. So in case strace is not enough for you, I would definitely use something like Wireshark, for example. So overall, strace is a very powerful tool which allows you to troubleshoot and debug programs without looking at the source code and without pausing the execution. It can attach to a running program, so you don't need to set up things in advance. The output can be not easy to interpret, but in many cases it gives you the general idea about what's happening, and quite often it's enough to find and fix a problem. Let's take a look at another very powerful tool, GDB, the GNU project debugger. You most likely know it if you've done coding in C or C++. Using it is similar to the way we used PUDB at the beginning of this talk, in a way that it's also a debugger which runs in your terminal. It also allows you to set breakpoints and list the source code if it's available. It also allows you to examine the stack and see the values of the local variables and call functions. But it's more than that. It has other very cool features. For example, you can do simple reverse engineering by looking at the assembly code of your program. Or you can reverse the execution of your program, which means that if you execute your program line by line, and at some point you just think that you've gone too far, you can sort of undo the changes and go back in the execution flow. GDB is so cool that it even has a song dedicated to it. However, most of these things aren't available or just aren't very useful to Python programs. But there are several very useful things in GDB that GDB can do for us, and one of them is attaching to a running program. First, you should install the GDB itself and Python debugging extensions. If you're using Python 3, then you should use the debug info package for Python 3. The Python debugging extensions package includes debugging symbols and adds several commands to GDB. Now, I'm going to emulate a program that is stuck. I'm going to run yum install zish, and when it prompts me to continue, I'm not going to do anything. So yum will just hang there, waiting for user input. And in another terminal, I'm going to attach GDB to the running yum process. First, there's going to be a lot of output from GDB, loading debugging symbols and complaining when some library doesn't have corresponding debug info package. And then we finally get the GDB prompt. Our program is paused at the moment, and we can use special Python commands to look around. Most importantly, we can look at the stack, the function called stack. We are using pybt command here, which stands for Python backtrace. I had to clean this output a little because it also shows local variables, and we just want to see the stack right now. Unlike PDB, it shows the stack trace with the most recent frame at the top. So at the very top, we see raw input function, and that makes sense because yum is currently waiting for user input. We can go up a couple of frames using pyup command, and we can look at the source code by using pylist command, and we can look at the state of our objects using pyprint command. But wait, didn't we do all of this in PDB? Why would we need GDB? Well, the thing is, if we want to use PDB, we have to think about it in advance. We have to add pdb.setTrace call to our program, for example, to drop to PDB whenever some signal is sent to our program. We can't just attach to any running Python application whenever we want without doing some prior changes to its code. And that's the awesome thing about GDB. We haven't made any changes to yum in advance, but we were able to attach to the process and see the stack and state of our objects. There are several tools that use GDB to attach to running Python processes. The most interesting of them is probably Pyrosite. Pyrosite allows to introspect and analyze running Python programs, and it works by injecting code in them. And it uses GDB for that. It comes with several useful payloads to inject, such as a payload for dumping out memory usage statistics, or forcing garbage collection, or building a call graph. And you can, of course, write your own code to inject. Now, let's take a look at the following example. Here I have a very useless multi-threaded program. I start 2 new threads, and each one gets its own function to execute. I'm going to run this program, and I'm going to attach to it using GDB. GDB knows about threads, and we can use info threads command to see the list of threads. The asterisk shows which thread GDB is looking at right now. We can switch between threads. We can run pylist to see the Python source code which is being executed in the current thread. We can also apply commands to several threads. For example, thread all apply pybt is going to print the stack trace for each thread. This is something we couldn't achieve in PDB. We can actually see more than just Python code in GDB. We can also examine the call stack and see the code on the C level. This way we can also debug C extensions, which our Python program is using, and that's something we often do because many components have functionality implemented in C. And if your Python application segfaults and dies, you can easily see both the Python and the C stack trace and find the extension that causes the segfault. It often happens that you can't reproduce the segfault yourself, but the users of your application can do that. So you can ask them to send you a code dump. What's a code dump? It's basically a snapshot of your process saved to a file. It contains a lot of information about the state of your process, including a memory dump. Let's see how it's created. Here I have a small artificial example program in Python. We are using string add function from the ctypes module. And this function returns the string starting at the memory address which we provide. And the program is going to segfault because it's trying to access memory address, which doesn't belong to our process. So if we run it, the kernel will send segmentation violation signal to our program, and it will terminate with a segmentation fault message. We can actually see that happen if we run it using strace, because as you remember, strace shows signals too. Now, chances are on your system a codedump file won't be generated because the shell sets a limit to the size of codedump files, and at least on my system it was 0 by default. So that can be fixed using ulimit command. Now, if we run our program, we see that the codedump file has been generated. We can now load it in GDB. To do it, we first specify the binary executable, which is Python, and then the codedump file itself. GDB loads it, and we can now do the post-mortem debugging on the codedump, just as we could do debugging on a running process. A few things to remember here is that you need the exact same executable as the one that was used to generate the codedump, and the same versions of the shared libraries used. Another thing is that even for our tiny little program, the codedump is 3 megabytes. And for a real program, it could be hundreds of megabytes or several gigabytes, depending on the program itself, because it dumps the memory that the process is using. By the way, you can also generate a codedump file for a running process. There's the Gcode utility that allows you to do it. But why would you want to do it? Well, if you want to take a look at a state of your running process, but you don't want to stop the process while you're doing it, you can generate a codedump file and load it in GDB to analyze it. Gcode is actually just a shell script which makes GDB attached to your process, generate a codedump, and detach from your process. Of course, that doesn't happen in an instant, especially if your process is really huge. Dumping the memory on disk will take some time. So I hope I've convinced you that in many cases, GDB is really great and really helpful, but I want to mention one more tool which can be useful in case you are dealing with segfaults. Maybe you don't want to go as deep and low level as GDB. Maybe it's enough for you to just see the Python stack trace at the time of a segfault. You can use fault handler module for that, and it's included in the Python standard library starting with Python 3.3, and on Python 2 you can install it using pip. There are several ways to enable it, and here I'm showing you the way that works for both Python 2 and Python 3. We just add 2 more lines to the beginning of our program. We import fault handler module and we enable it. And when we run the program, we get a nice Python stack trace. And it's quite possible that in our case it's enough. Okay, let's summarize. When everything else is unavailable, you still have your standard library. It's always there for you. You can use your PUDB debugger. You can have a simple tracer to trace the execution of your program. You have several profilers to analyze the performance of your application. Python 3.3 includes the fault handler module to help you see the stack trace if some catastrophic event happens. And Python 3.4 has the trace-malloc module, which traces memory allocations, so you can find out if you have any memory leaks. So right out of the box, you have very powerful debugging tools. If you don't usually use a debugger, give it a try. I prefer using PUDB, but there are a few options available. Some of them provide really comfortable experience and nice features, like the PyCharm IDE debugger, for example. Using a debugger makes it easy to quickly get familiar with this piece of code and find out exactly what's wrong and even test your fix right there in the current context. Your Linux kernel can provide a lot of help. There's a special system call named ptrace, which is exactly what allows other programs attached to your running process, such as strace and GDB. Strace allows you to see what an application is doing, even if you don't have the source code. Many other monitoring tools exist, such as lsoff, which rely on the information from the Linux kernel in the proc directory. GDB may not be something you will use on a daily basis, but there are certain use cases where nothing else will help you. With Python debug info extension, you can use GDB to analyze your running application, look at the current stack trace and the values of the local variables, and you can do so for each thread. If your Python application relies heavily on modules implemented in C, then you will definitely want to use GDB. And that's all I have. If you have any questions or comments, please come talk to me or send me an email or contact me on Twitter. And thank you for your attention.
Thank you for your excellent talk. I have a question about the PUDB. If I am correct, it uses Urwit to display draw the interface. But if you stack with another platform, I think Urwit is only available for Linux. And if you stack with Windows, and would you recommend something which can run in the console? I know only about WinPDB on Linux, which is graphical.
Yes. Sorry, I don't know much about Windows. If I was on Windows, I would be probably using something like PyCharm.
Yes, great. Me neither, but it was interesting for me because there are no encoders and similar things. So if there even is another textual debugger.
There probably is something. I'm just not prepared to answer to.
Thank you.
Yes.
Thanks for the talk. I have two questions. The first one is, I really like the strace stats, the -c output.
Yes.
So is there something similar that would allow us to see stats about Python functions, how they are running or using the CPU?
Definitely. The C profile module that I mentioned, it's a profiler.
C profile, right?
Yes,
Okay.
you can use it to generate that kind of statistics. And there are even utilities like run snake run or something that shows you visualizations of all of that. So yes, you need a profiler for that, yes.
And my second question is, you told that, or I saw that you installed with GDB, you installed also the Python debug symbols.
Yes.
So I have to do this in advance.
No.
No, I can attach to a process and use the fancy PyGDB
yes,
commands?
As far as I know, you can. At least when I tried that many times, that worked.
Okay, great. Thank you.
Thanks. I like the talk as well. How do you in your work deal with the, you have to have exact same environment as the user who sends you the core DOM, especially if they use some exotic and weird libraries they have to have on their system. Do you have some recommended way to handle that, or do you just work around it?
As far as I know, there are utilities for that, but we usually just ask questions like, which libraries versions are you using? There are definitely utilities for collecting that information about the environment.
Do you have a way to basically install those libraries if you need them for debugging? Can you just have some test VM somewhere and install it, or are you just working with the strace output, or what do you have? So if somebody uses a commercial library that happens to be loaded in the process and you can't have it, have you seen that?
They are out of luck probably.
Okay.
Not a question, but a small addition to the toolset. Maybe more user-friendly than strace for the average developer is a sysdig. It's currently developed outside of the kernel, and you can install it with as an external module and allow do pretty much the same what strace does, plus extra LSOF and few other tools. combined in one much nicer and cleaner way for the end user. It's just much better user-friendly.
Yeah, I didn't catch the name.
Sysdig.
Okay, well, if you could send it to me.
Yeah, okay.
Thank you.
Anyone else?